Well, hey, folks. We are starting the day 24 material. We're looking at a topic called stable marriages, and in a moment, we'll try to clarify what that means in a mathematical context. Before I start that, I want to show this screenshot from YouTube. This is Monday's video. I'm recording this on Wednesday morning now. In fact, I'm wearing the same shirt. I'm not proud of that. Um, and one of the things I want to mention here is that we have only 27 views um, on Monday's video. You've had 48 hours now roughly 48 hours to watch this, and only about a quarter of you have done so far. I'm, I get that people are busy and fall behind, but in particular, today's video is a follow-up from what we did last time. And so marriages are a type of matchings. And so if you have not watched day 23, you need to watch this first. And so don't try to watch these videos out of order. I think that's just going to confuse you. So um, I want to see this number go up a little bit before today's number starts going up. All right. Um, let's go ahead and get started. So if we have a bipartite graph with partite sets x and y, so we've got vertices over here in x and some vertices over here in y. If we have a matching that uses every vertex in x, even if there are vertices in y that are left over, so I can match every vertex in x to a different vertex in y, then we can say that x can be matched into y, okay? So that means that y has to have at least as many vertices as x, but that's not always going to be enough, and we'll see an example of that in a moment. So in this graph here, K3, 2, 3 vertices in x and 2 vertices in y, I can match vertices from y to x, and there's a vertex that's left over, but I can't go the other way or match vertices from x to y because once I've matched two of them, there's no place for the third one to match. So y can be matched into x, x can't be matched into y. But here's a bipartite graph where I have enough vertices to go in both directions, but I can't match x into y because this vertex will only match to the top one, and this vertex will only match to the top one. And so I can't satisfy both of these two vertices. And in the same way, this vertex will only match downwards, and so will this vertex. And so there's no way to satisfy both of these vertices. And so I can't match x into y, and I can't match y into x, even though they have the same number of vertices. And so, so we're going to look at the question, is it possible, what conditions is it possible to match x into y? And the requirement is that if I look at any set of vertices in one of the partite sets, then that set has to have at least as many neighbors as the set. So let's go back to this example here, and I will clear off the annotations for a moment. And let's look at how Hall's theorem would work with this. So I start out with this vertex. I've got one vertex in x. And I look at its set of neighbors, and there's one vertex over here in y. Well, that's okay because 1 is less than or equal to 1. But then if I expand this set down here, now we have two vertices in x. But if we follow the edges over and look at their neighbors, there's still only one vertex in y. And that's not okay because 2 is not less than or equal to 1. Well, if we kept going to 3 vertices in X, now we have 3 vertices in X, and we look at the neighbors, and this vertex down here neighbors to everybody in Y. And so we have 3 vertices in Y. And again, that's okay because 3 is less than or equal to 3. But Hall's theorem says that all of these have to be okay. That so that this has to be true for all subsets in X. And the inequality that the neighboring set has to be at least as large is not true in this case. The neighboring set is smaller. So that's what Hall's theorem says. We have to have at least as many neighbors as vertices for all subsets of vertices in X. Okay? So the proof for this theorem is by induction. So we're going to start with the base case. So your base step is assume X has only one vertex. Well, since X has one vertex, then that vertex has to have at least one neighbor by the condition. So we'll call that V. Then the neighboring set of V has at least one vertex. W, and then VW is a matching. From X into Y. We only had to match one vertex, and if S has one vertex in it, then N of S has to have at least one vertex in it, and so we match this for 2 vertices together. All right, so let's move on. So let's look at the induction step. Assume that for all integers from 1 to n, if X has k vertices, and this condition is satisfied, then X can be matched into Y. We're going to assume then that let G be a graph in which X has k plus 1 vertices, or n plus 1 vertices. But still satisfies this condition. And NS is greater than S for all S subset of X. Okay? All right. we're going to look at two cases. So, case one. Suppose we could drop this equal sign. Suppose ns is greater than s for all s in x. Okay? Pick any vertex in x. Okay? Then, because I'm taking only one vertex out of this set, then how do I want to say this? Pick any vertex x and v and x, match it to any adjacent vertex w in y. Okay? So I'm picking a random vertex v, matching it to vertex w and y. Okay? Let G star be the graph G minus the set VW. Okay? So I'm deleting one vertex in X and I'm deleting one vertex in Y. Okay? Now in G star, where'd my pen go? There you go. N of S will be greater than equal to S. And here's why. For any subset of X, and I look at the neighbor of the subsets, this was true in the original graph. All right, if I dropped X from S, then this gets smaller by 1. But if I dropped Y from the neighboring set, then this set gets smaller by 1. Now, if both sets get smaller by 1, the inequality stays the same. If this set gets smaller, but this one doesn't, the inequality still stays the same. If the one on the left gets smaller, but the one on the right doesn't, these might not be greater than anymore, but they'll still be equal, because I'm only decreasing this by 1. And so I don't know whether these sets contain X or Y, but in every case, the inequality will hold or it might drop down to just being equal. Okay? And so G star has a X can be mapped into Y. Let's be specific about this. X minus V can be mapped into Y minus W, and therefore X can be mapped into Y. Because we've already mapped V and W each other. So, all right. I'm using the word mapped here. I should say matched. So let me correct that. There you go. All right. So let's look at case 2. there is some set S that we cannot make the inequality sign go away. So there is a set S for which the number of neighbors in S is equal to the number of neighbors of S. Okay? All right. Well, in that case, come on, there we go. All right, there's a set S for which S is equal to NS. Then X minus S is equal to the neighbors of. All right. This is also going to be true, it turns out. And why is this true? If I had some vertex at X minus S that mapped into this other set, then S plus that vertex would map into a smaller set and would not satisfy this this condition. Then we would have S being larger than n of S. So we have to have this as well. Okay. And so what happens now is we've got this original graph. Here's sort of my picture. I have X and Y. And I've had to split X into two sets, S and X minus S. But because S is a subset of X, we can apply Hall's theorem and get a matching of those vertices. And then because X of S also satisfies this, we could get a matching of those vertices. And then if we take the union of those two matchings, then we get a whole thing. So by induction, S can be matched into N of S, and X minus S can be matched into N of X minus S. Because each of these sets is smaller than the original set, and therefore, by the induction hypothesis, if K is less than N plus 1, then we can do this. So this is where we're using the induction hypothesis, is we're applying the induction to the smaller sets S and X minus S. Then the union of these matchings is a matching from X to Y. All right. So case 2 is a little harder to prove than case 1, but this finishes up the proof of Hall's theorem. All right. So let's look at stable marriages here. So in 1962, David Gale and Lloyd Shapley published this paper, and it looks at this sort of socially dated question. It's sort of awkward to talk about now because of the assumptions that were being made about, how people married up in 1962. But The hypothesis is we want to arrange marriages between N men and N women, and every marriage has to consist of one woman and one man. And the men have ranked the women in order of preferences, the women have ranked the men in order of their preference, and we say that we have made a stable assignment if even if somebody didn't get their first choice, um, there is no pair of there's no man and woman that's preferred that's matched up to each other that would uh, there's no mutual preference that would be better. That's the idea. Um, so let's look at this example. So this is these are four males, A, B, C, and D, and their preferences are listed here. So A's first choice was W, and B's first choice was W, and C's first choice was W. Apparently, W is quite a catch, but D's first choice was Z. And then here are W, X, Y, and Z's list of preferences. A is W's first choice, B is X's first choice, and so on and so forth. Okay? So this is not a stable assignment. But let's look at what happened. A and W are going to be stable because they got their first choice. So this is stable. B and X, X got her first choice. B did not get his first choice, but A and W preferred A over B. In fact, B would have been W's very last choice. And so B got his second choice, but is going to basically have to put up with that because B has no hope of getting W to leave A for him. So that's the idea. So this is also stable. All right. But look what happens here. C is currently matched to Y, who is C's third choice, and C would prefer to be with Z. So C would rather be with Z. And let's look at what happened here. Z is matched with D, but D was Z's third choice. Z would rather be with C. And these people agree. That is, C is saying, I would leave my wife for you. And Z is saying, I would leave my husband for you, because both of them are saying they prefer these two people over their current partners. And so these marriages are unstable because there is a mutual preference that has not been recognized. Is everybody understanding why that works? And so if we were to assign these four marriages, this would not be a stable assignment, because C and Z would leave their partners because they prefer each other instead. Okay? So it's mutually agreeable among C and Z. It's not so mutually agreeable among Z and D and Y. Y would rather be with C, and D would rather be with Z, but they don't have any say in the matter. That's the idea. All right. So I don't know why I've got this in such a narrow column and it got cut off, but anyway, Gale and Shapley proved in 1962 that a stable assignment was always possible. And but their assumptions were that the number of men and the number of women were identical, so that they were only looking at sets that had the same cardinality. And they were also assuming that well, they were looking at the marriages here. So this algorithm that they proved was possible in the restricted case where n and n are equal and we're matching 1-to-1, had found use outside the field of heterosexual matchmaking. 50 years later, this was 1962, where Shapley was working for Gale. I mean, was sort of interning with Gale in Gale's research group. Gale has passed away, and now Shapley, who is now sort of much older. So this is 50 years later, 2012, working with a different mathematician named Alvin Roth, adapted this algorithm to a different problem, the problem of matching medical schools and residencies. So that changes the circumstances, that the marriages don't have to be 1-to-1. We can match, we can have a medical school that accepts multiple graduates. And we don't have to have exactly the same number. We could have more graduates than spaces available, or more spaces available than graduates. And so, Shapley and Roth improved upon the Gale-Shapley algorithm to match this up. And this is how the National Residency Matching Program works. And so what we're going to look at today is the 1962 version of this proof. The 1-to-1, same number of people cases. And then later on, we're going to look at how do we have to adapt this for the improved 2012 version of this algorithm. So we're looking at the quaint Gale-Shapley version. So we choose one group to be the proposers and one group to be the proposees. The proposees all stand in a line and passively wait to be proposed to. And each proposer goes up to their first choice and proposes marriage. And that means that some proposees may have multiple suitors, some may not have any. And, well, that's okay. Each proposee says yes or says maybe to their highest preferred suitor and no to any other suitor. And any suitor that receives an answer of maybe stays with the proposee. Any other suitor that receives an answer of no goes back to the stag pool. If the stag pool is empty at the end of the round, well, if it's not empty, we just start a new round where every proposer in the stag pool crosses off their first choice. They got rejected by their first choice. They go on to their second choice and approach that proposee, and keep going. So here's an idea. We're going to apply the Gale-Shapley algorithm to find marriages among these 10 people, and here are their preferences. Okay. And what we're going to do first is we're going to let the men be the proposers. This is probably what they were thinking at the time. So the men propose, and the women just wait. All right. And so let's look at what happens. In round one, the women, who are Wanda, Wanda, sorry. These have similar names. I got this out of the Harris textbook. Wendy, Wilma, and Winnie. They're just standing in a line, waiting to be proposed to. And each man comes up and lines up by their first choice female and proposes marriage. So Mac lines up with Winnie. Mark lines up with Wanda. Marv lines up with Winnie. Milt lines up with Winnie. And Mort lines up with Wanda. All right, so each man has made their declaration now. And the women get to make a choice out of their potential suitors. So Wanda has to make a choice between Mark and Mort. So Wanda, here's Wanda in the second row. Here's Mark, and here's Mort. Well, Mort is Wanda's third choice, but Mark is Wanda's fourth choice. And so Wanda is going to say no to Mark. So that crosses Mark off of this row, and it crosses Wanda off of this row because Wanda has said no to Mark. And right now she's just saying maybe to Mort because she's hoping that one of these other two people, Marv or Milt, will come and propose to her later. But in round one, she says no to Mark. All right, so let's look at what Winnie does. She's got three suitors, Mac, Marv, and Milt. Marv is her first choice. And so she's going to go ahead and say, yeah, I like you, Marv. And send Mac and Milt back to the stag pool. And so Mac and Milt do not get paired with Winnie. All right. And so round one, we have two people who are partnered up and three people who are back in the stag pool. So in round two, those three stags, Mac, Mark, and Milt, have to propose to their second choice. So now Mac lines up next to Wilma. Mark lines up beside Winnie. And Milt lines up beside Wilma. All right, so Wanda only has one person in front of her from round one, and so nothing changes here. Wilma has two people in front of her and has to make a choice between Mac and Milt. And so here's Wilma. Mac is her fourth choice. Milt is her third choice. So she is going to say maybe to Milt, hoping that maybe one of these other two gentlemen will ask her instead. But she's definitely going to say no to Mac. So Mac got rejected a second time and goes back to the stag pool. Winnie has two people standing in front of her, Marv from her first round and Mark from the second round. But again, Winnie prefers Marv. Marv is her first choice, and so she's going to reject everybody else. She's going to reject Mark. And so Mark did not get his second choice either, and he goes back to the stag pool. All right, so now we have two people in the stag pool. Mark and Mac, those are the two people who had their second choices rejected. And so now in round three, they approach their third choice. So Mac is going to approach Wanda. And Mark is going to approach Wendy. Well, nobody else has approached Wendy yet. And so Wendy doesn't have to make a choice, doesn't have to make a choice between two suitors. But Wanda does. Mort has been standing there since round one, and Mac just showed up and says, hey, I like you. And So Wanda looks and says, well, Mort is my third choice, but Mac is way down here, my very last fifth choice. And so Wanda's going to send Mac packing, and Mac just lost his third choice partner. Okay. So we go to a fourth round. And this time Mac asks Walda, who's been sitting over here and nobody has proposed to her yet. And so Walda doesn't have any better offers, and so she says maybe to Mac, but nobody is left in the Stagpool now. And so all of these matches get finalized. Mac gets paired up with Walda. Mort gets matched up with Wanda. Mark gets matched up with Wendy. Wilma gets matched up with Milt. And Marv gets matched up with Winnie. And they really are the happiest couple here, I think, because they got their first choice. So that's what ended up happening. Okay. All right. So that is a stable arrangement. It's stable because every man has tried approaching their preferred women and were turned down every single time. And so no man is going to be able to leave the woman that they are married with now because anybody that they would prefer has already rejected them. That's the idea. And it's not been the case that the women have been rejected by their higher choices, but no man that is a higher choice for a woman would say yes. Let me explain why. For example, Walda would rather be with Mort than Mac, but if Walda were to secretly approach Mort, Mort is already with his first choice and would say no to Walda. If she were to secretly approach Milt, Milt is with his second choice, but Walda was his fifth choice, and so he'd say no also. And so nobody can trade up. Is what would happen if anybody tries, they would be shot down. Okay, so that's a stable matching. Mac to Walda, Mark to Wendy, Marv to Winnie, Milt to Wilma, and Mort to Wanda. So let's do the same problem again. This time, since we had men proposing to women the first time, we'll do this the other way around. We're going to have women proposing to men. Okay? So this time, the women propose, and the men are waiting. All right? So here are our men: Mac, Mark, Marv, Milt, and Mort. There you go. And let's look at what happens in round one. This time, the women line up behind their first choices. So Walda approaches Milt. Wanda approaches Milt. Wendy approaches Mort. Wilma approaches Mark. And Winnie approaches Marv. So the only man who has to make a choice in the round one is Milt. And Milt has to choose between Walda and Wanda. And since Walda is his third choice and Walda is his fifth choice, he says no to Walda. And so Walda cannot pair up with Milt. So Walda goes back into the stag pool and lines up behind her second choice. And her second choice is Mort. And now Mort has to make a choice. Stay with Wendy, who approached him in round one, or go to Walda instead. And Mort looks at his preferences, and Walda is his third choice, but Wendy is his fifth choice. And so Mort is going to switch partners now, is going to rule out Wendy. So Wendy is no longer with Mort and hold on to Waldo now. So now Wendy has had her first choice rejected. So the next round, Wendy has to go to her next choice. And that would be Mac. And so Wendy would approach Mac. And now nobody has a choice to make. And so everybody will take their choices. So Wendy gets Mac. Wilma gets Mark. Winnie gets Marv. Milt gets Wanda, and Mort gets Walda. Or if we circle them up here, Mac got Wendy, who was his very last choice, but the only one who asked. Mark got Wilma. Marv got Winnie. Milt got Wanda, and Mort got Walda. Okay? All right. One of the things I want to notice here is that when men did the proposing, 3 of the 5 men got their first or second choice, and only 1 of the women got their first or second choice. But when women did the proposing, all 5 women got their first or second choice, and only 1 man did. And so there is an advantage to being the proposer. That's one of the things that came out in this algorithm, is that being first, being first and approaching the partners that you prefer, gives you an advantage. You're in the ring with that partner at that point, and nobody else may be approaching that partner yet. And so there is a difference between a tradition in which men are doing the proposing and a tradition in which women are doing the proposing. The outcomes are more satisfying for whichever group is doing the proposing. So that is not surprising. That, in fact, has been proven to always happen. Okay, so both of these are stable partnerings, but one is much more satisfactory for the men, and one is much more satisfactory for the women. All right. So then what happens when women propose to men? Okay, so we did men and women. We just did them on the wrong slides. We went ahead and did this. All right. So let's, oh, shoot. This has gotten cut off because of what's going on here. Let me pull this up here. I'm going to fix that table for a moment. Bear with me. There we go. All right. Okay, so we have this example with just 4 men and 4 women. Um, and the bottom row of the women's table is cut off here, but I think we can see it on this next slide here. There we go. Um, so if we use the women as the proposers, let's determine a stable perfect matching for these 8 people. Okay? So women are doing the proposing, which means the men are going to be just standing around waiting for things to happen. So those are Adam, Alan, Aldo, and Alex. All right, so let's look at round 1. All the women approach their first choice. So Bala approaches Adam, Barb approaches Alan, Beth approaches Aldo, and Bree approaches Adam. And so Adam has to make a choice, and Adam prefers Bree over Bala, and so says no to Bala. And so Bala is without a partner right now, so she goes to her second choice, who is Aldo. And now Aldo has to make a choice between Bala and Beth. But Aldo is very excited because Bala is who he wanted to be, and Beth is his least favorite partner. So Aldo says no to Beth, and now Beth is without a partner. So she goes to her second choice, which is Adam. And now Adam has to make a choice between Bree and Beth. So um, Beth is Adam's second choice, and Bree is his third choice. So Bree, who's been waiting there earlier, this was round 2. We're now in round 3. Bree then goes back into the stag pool for a 4th round. So Bree got rejected by Adam, so she approaches Alan. All right. And so now Alan has a choice to make, Barb versus Bree. Barb versus Bree. Barb is Alan's preference over Bree. So Alan rejects Bree. So Bree goes back into Stagpool. Now we're at round 5, and Bree approaches Aldo. It was now her third choice. But Aldo says no because Aldo was already with his first choice. And so Bree doesn't get to match up with Aldo. So Bree approaches Alex. And Alex has been standing there waiting all this time, and nobody else has approached Alex. So, but Bree is going to end up with Alex because all 3 of the other men have turned her down. Okay? So this is going to be our pairing. Bala goes with Aldo, Barbara goes with Alan, Beth goes with Adam, and Bree goes with Alex. Okay? So Adam ended up with Beth. Alan ended up with Barb. Aldo ended up with Bala. And Alex ended up with Bree. All right. So that's what ended up happening. Okay. So let's move on. Same table, but let's see what happens if the men are doing the proposing. So now the women are going to be waiting. Bala, Barb, Beth, Bree. All right. In round 1, each man approaches his first choice. So Adam approaches Barb. Alan approaches Bala. Aldo approaches Bala. and Alex approaches Beth. And so Bala has a choice to make, but she prefers Aldo over Alan. And so Alan gets rejected. And so now Alan has to approach his second choice. So Alan approaches Beth. And now Beth has a choice to make. But Beth prefers Alex over Alan. And so Alan gets rejected a second time and approaches his third choice, who is Barb. And now Barb has a choice to make, but she preferred Alan. And so she sends Adam away. And so Adam just got rejected by his first choice. So Adam now has to approach his second choice, Beth. And Beth prefers Adam over Alex. And so Alex gets rejected by his first choice. And so Alex has to approach his next choice, who is Barb. And now Barb has to choose between Alan and Alex, but Barb is already with her first choice. And so she's going to reject Alex. And so Alex just got rejected by Barb, so he approaches Bala. And Bala prefers Aldo over Alex. So Alex is still being turned down. And so Alex has to approach his fourth choice, who is Bree. And nobody has approached Bree yet. And so Bree goes ahead and accepts Alex. So this is the pairing that we end up with this time. So Bala matches with Aldo. Barb matches with Alan. Beth matches with Adam. And Bree matches with Alex. Okay. All right. Thanks for watching. What we'll look at next time is how do we modify this algorithm to handle the cases of multiple resonance applying to a program. All right. Take care.